Right now, you're probably looking at a screen, scrolling with your thumb, or holding a phone, a cup of coffee, or a pen. And the last time your fingers touched a surface, felt the texture, or gripped an object, you probably just did it and felt it and forgot about it. But what your fingers just did is one of the most mechanically complex things a biological organism can do. It's more sophisticated than any touchscreen, more sensitive than any sensor on a robotic arm, and the tiny ridges on the tips of your fingers, your fingerprints, actually hold a secret that rewrites everything we thought we knew about why humans evolved to touch the world. Because our relationship with fingerprints doesn't start a few thousand years ago with the invention of wine or the first clay signature. It starts about 55 million years ago in the dark, wet canopy of an ancient forest with a small primate reaching out to grab a branch in the middle of a rainstorm. For over 100 years, the story we were told in school was incredibly simple. You have fingerprints because they increase friction. They act like the treads on a car tire, channeling away moisture so you can grip objects without dropping them. It makes intuitive sense. But in 2009, two biomechanics researchers at the University of Manchester named Roland Innos and Peter Warman decided to put this to the test. They built a custom machine in their laboratory, strapped a student's finger into a device, and dragged a smooth sheet of acrylic plastic, perspex, across the skin, measuring the exact force of the friction. If fingerprints existed to increase grip, then pressing harder should have generated significantly more friction. But the results were baffling. Because human skin is soft, elastic, and rubbery, fingerprints actually reduced the friction by up to 33% on smooth surfaces. By creating deep valleys between the ridges, our fingerprints cut down the actual physical contact area between our skin and the object we are holding. Honestly, on a smooth surface like a glass table or a modern smartphone screen, having fingerprints actually makes your grip worse. It makes you more likely to slip. Yeah, think about that. Up until this discovery, the story went like this. Humans settled down, evolved fingerprints as a mechanical handle to help us grip tools, hunt, and build. Friction came first, and touch sensitivity was just a byproduct. But the Manchester study suggested the exact opposite. If fingerprints aren't a handle, what are they? They are amplifiers. To understand why, we have to look about 2 millimeters beneath your skin. Sitting in your dermis is a highly specialized network of sensory receptors called Pacinian corpuscles. They look like microscopic onions made of 20 to 60 concentric layers of tissue wrapped around a nerve ending. These corpuscles are incredibly sensitive to high-frequency physical vibrations, specifically between 80 and 400 hertz. In 2009, a group of physicists in Paris, led by Dr. Georges Debrajis, wanted to know how our skin detects fine textures, things like the difference between silk and paper, or a micro crack in a stone tool. They built a mechanical tactile sensor, capped it with a ridged rubber skin to mimic a human fingerprint, and dragged it across various textured surfaces. What they discovered was remarkable. As your finger slides across a surface, your fingerprint ridges don't just glide smoothly. They physically stutter, jump, and bounce over the microscopic terrain, generating tiny, rapid micro vibrations in your skin. The researchers found that the physical spacing of our fingerprint ridges acts as a biological tuning fork. As your finger moves, the ridges compress and stretch, converting the friction into a vibration frequency of precisely 250 hertz, which happens to be the absolute sweet spot for your Pacinian corpuscles. Without those ridges, the vibrations would be muffled and lost in the soft, fatty tissue of your finger. But with them, your sensitivity to textures is amplified by up to 100 times. It allows you to feel textures that are less than a fraction of a millimeter wide, like a single human hair lying on a flat table. And for our ancient ancestors, this was a matter of life and death. If you are a small nocturnal primate swinging through branches 55 million years ago, you can't afford to look at every branch or leaf before you touch it. You are hunting in the dark. You need to instantly know, within milliseconds of touching a surface, whether a branch is dry and sturdy or wet, rotten, and about to snap. You need to feel the subtle, waxy texture of an edible leaf versus a tough, toxic, unripened one. Your fingerprints allowed you to see the forest canopy in high definition through your fingertips long before your eyes could register the details. But there is a second, even more
remarkable feature built into your fingers, and it solves the moisture paradox. In 2020, researchers at the University of Birmingham published a study in PNAS looking at how our fingers handle water. If you look closely at your fingerprints under a microscope, you will notice something peculiar. Your sweat pores are located exclusively on the peaks of your fingerprint ridges, never in the valleys. This creates a highly optimized, self-regulating moisture valve. When you touch a dry, smooth object, your skin is naturally stiff, which reduces your grip. To fix this, your nervous system triggers the sweat pores on your ridges to secrete micro droplets of moisture. This moisture plasticizes the skin, softening the ridges so they flatten and conform to the surface, maximizing your grip. But what happens if you grab a wet, muddy branch? If too much water gets trapped between your finger and the object, you will suffer from aquaplaning. The water acts as a barrier, and you lose your grip completely. This is where the valleys of your fingerprints, the furrows, come into play. They act as microscopic drainage channels. When you squeeze a wet object, the excess water is siphoned away into the valleys, leaving the peaks of your ridges dry enough to make direct, firm contact with the surface. If you're working in a wet forest or trying to climb a slippery rock face, your fingerprints are actively regulating moisture on a millisecond scale, adding sweat to dry surfaces to increase grip and siphoning away excess water on wet surfaces to prevent slipping.
And we aren't the only ones who figured this out. Because this system is so incredibly successful, evolution came up with the exact same design in completely different parts of the animal kingdom. Koalas are marsupials. They're separated from humans by over 70 million years of independent evolution. Yet koalas have fingerprints on their paws that are so structurally similar to ours that even under a scanning electron microscope, trained forensic scientists can have difficulty telling them apart. Why? Because koalas also live in trees, move through wet canopies, and need to feel the exact oil content of eucalyptus leaves before they eat them. Furthermore, some South American spider monkeys have evolved similar friction ridges not on their fingers, but on the very tip of their prehensile tails, turning their tails into a fifth highly sensitive slip-resistant hand. So here's the full picture. 55 million years ago, your primate ancestors evolved friction ridges to navigate the ancient canopy, using micro vibrations to feel their way through the dark forest. 70 million years ago, koalas independently evolved the exact same patterns because they shared the same survival challenges. 2009, researchers in Manchester proved that fingerprints actually reduce friction on smooth glass, completely dismantling the old tire tread myth. 2009, physicists in Paris showed that fingerprints act as a physical amplifier, tuning vibrations to match the sensory receptors beneath our skin. 2020, scientists in Birmingham mapped the sweat pores on our ridges, revealing a self-regulating moisture valve that prevents slipping in wet conditions. Our fingerprints didn't evolve so the police could catch us, and they didn't evolve so we could unlock our smartphones with a touch. There's a real possibility that we have them because they're the very reason we were able to interact with the physical world, develop fine motor skills, and build the tools that created human civilization. Without the massive sensory feedback loop provided by our fingerprints, our brains would never have developed the complex hand-eye coordination required to carve stone, build fire, or write our history. Every time you swipe a screen, touch a smooth piece of wood, or grab a glass of water, you are continuing a physical conversation with the world that started before your species had a name for itself. Tools changed, the screens got flatter, the technology got fancier, but the touch engine is the exact same one that kept a small primate alive in a tropical storm 55 million years ago. We just learned how to use it on glass.